friends, welcome to our YouTube channel Naraj Academy. The main aim of this lecture is to discuss about the communication systems prelims questions of the ESE of previous year in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button so whenever we upload a new video, the direct notification comes on mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to solve the 121 question. See the question here. For a 10-bit PCM pulse code modulation system, the signal to quantization noise ratio is 62 dB. So if the number of bits is increased by 2, then how would be the signal to quantization noise ratio change? So in the question, when n is equal to 10 bits in the PCM, the signal to quantization ratio in dB is 62. Suppose if the number of bits is increased to 2, means the number of total bits is 10 plus 2, which is 12. So when n is equal to 12, we need to find what is the signal to quantization noise ratio and how much is the change we need to figure out in dB. So what are the four options? Option C increases by 12 dB. So let's solve this numerical. So in PCM, the signal to quantization noise ratio in dB value, which is 6n plus 1.8. This is in dB value. So therefore here in the question they are given when n is equal to 10 bits. See, when n is equal to 10 bits, we need to find what is the signal to quantization noise ratio, and when n is equal to, when n is increased by 2, means 10 plus 2, which is 12, then we have to know which one is greater by how much units. So therefore, if I substitute n is equal to 10 here, the signal to noise ratio in quantization noise ratio in dB, so in place of n, substitute here 10, so 60 plus 1.8, and similarly, when n is equal to 12, substitute here 6 into 12 is 72 plus 1.8 dB. So now do the subtraction of second minus first. So SNR2 minus SNR1 is equal to 72 plus 1.8 minus 60 plus 1.8. So 1.8 get cancels. 72 minus 60 is equal to 12 dB. So therefore we can conclude that the signal to quantization noise ratio of the second one is 12 dB higher than the previous one, than the first one. So therefore we can conclude that the signal to quantization noise ratio when n is equal to 2, means when n is equal to 12, which is the second part, is always 12 dB more than the first part. So therefore we can say it increases by 12 dB. It is a correct solution of this question. So now we are going to solve the 132 question. See the question here. Voice is digitized using an ADC with a sampling period of 0.1 millisecond and 10 bits per sample. So what is the bit rate in kbps generated by this system? So ADC is nothing but this is used in the PMC, pulse code modulation. So therefore here in the question they are given that the sampling period TS is nothing but 0.1 millisecond, and also they are given that n is equal to 10 bits per sample. So for each and every one sample, the number of bits which you are going to use is 10. So now we need to find what is the bit rate means. So the bit rate means number of bits per second, how many bits are being passed, we need to figure out from this system. So out of the four options, option A 100 kbps is the correct solution of this question. So let's solve this numerical. So in the question they are given that the sampling period is 0.1 millisecond, and also they are given that the number of bits per sample is 10. We need to find what is the bit rate for this one, we need to figure out. So basically the bit rate means the number of bits per second, how many number of bits per second which are passed, we need to figure out. So basically the sampling frequency is equal to 1 by sampling period. So 1 by 0.1 milli means if it goes up it will become kilohertz. So 1 by 0.1 is nothing but 10 kilohertz. So therefore the sampling frequency means the number of samples per second is nothing but 10 kilohertz. So we need to find what is the bit rate. So bit rate is the product of the number of bits per sample and the sampling frequency, n into fs. So n into fs is nothing but bit rate. So the value of n we know, which is 10, and the value of the fs is 10 kilohertz. So if you solve this one, we are going to get 10 into 10 is nothing but 100 kbps, means kilobits per second. See the unit of n is nothing but the unit of n is the number of bits per sample, and the unit of fs, the sampling frequency, is nothing but number of samples per second. So if you do the multiplication of both these things, the sample is going to get cancelled. So therefore bits per second is going to remain. So therefore the unit of the bit rate is nothing but bits per sample. So these many number of bits are being traveled in 1 second. So therefore 100 kbps is the correct solution of this question. So basically n is nothing but the number of bits per one sample, and also fs is nothing but sampling frequency, and we can also say that number of samples per second. So finally the bit rate is nothing but n into fs. So the final solution is 100 kbps. So now we are going to solve the 123 question. See the question here. So what are the 3 steps in generating PCM in the correct sequence? So we need to find what is the correct sequence which is used in the PCM. We need to figure out. So what are the 4 options regarding the sampling, quantizing and encoding? We need to know what is the correct sequence. So what are the 4 options? Option A is the correct solution of this question. Means first thing we are going to do the sampling, and then we are going to do the quantizing, and then we are going to do the encoding. So let's solve this question. So this is a block diagram of the PCM transmitter, pulse code modulation. It is a digital communication, means it has the highest noise immunity when compared to remaining all other schemes in the analog communication and the digital communication. So therefore always the digital communication has a more noise immunity, and among them the PCM has a more noise immunity when compared to remaining all other schemes. So therefore here this is the block diagram of the PCM. See, the M of t, the message signal M of t is an analog signal. So first we are going to use a sampler. Means with the help of sampler, means the sampling frequency the sampling frequency should be greater than or equal to twice the maximum frequency of the message signal. So we have to sample like this. So therefore, see, whatever this is analog signal. So finally we are going to get in this manner, like impulses we are going to get of different amplitudes we are going to get. So this is the nature of the signal in this area, and then we are going to use a quantizer. So because here there is an infinite number of amplitudes we can get here. So by using the quantizer we are going to fix the standard levels. Suppose it is 0.29. So now I am going to assume a standard level of 0.5. So therefore it will become now 0.5. Suppose this is 0.30, then also it is going to become a 0.5 because it is a standard level. Suppose if it is 0.36, then also by using the standard level it will become again 0.5. So all these signals in this range can become now standard value 0.5. So with the help of this, in the initial phase after the sampler we can get infinite number of amplitudes. So by using the quantizer we are going to fix a particular fixed standard levels. So with the help of this we can decrease the number of amplitude levels. So therefore this is we are going to with the help of quantizer. And then for each and every sample of fixed standard level we are going to convert in terms of a binary digit n bit data. So each and every sample now we are going to represent by n bit binary data. This we are going to do with the help of the encoder. So this is the binary signal. So now this binary signal we are going to transmit through the channel. So therefore first thing is here in the PCM transmitter, first thing is we are going to the sampling process, and then we are going to the quantizing process, and then we are going to do the encoding process. So this is a correct sequence. The first thing is sampling, then we have to do the quantizing, and then we have to do the encoding process. So now we are going to solve the 124 question. See the question here. Good voice reproduction via PCM requires 128 quantization levels. If the bandwidth of voice channel is 4 kHz, then what is the bitrate? So in this question, the PCM they are given the standard levels. The number of standard levels required is 128, and also the bandwidth of the voice channel means 4 kHz. Then we have to find what is the data rate or bitrate we need to figure out. Means the number of bits per second, how much we need to figure out. So what are the 4 options? Option C, which is 56 kbps, means kilobits per second, is the option C is the correct solution of this question. So let's solve this numerical. So here in this question, the L represents the number of standard or quantization levels. So here n is the number of bits per sample. So with the help of n bits, we can make the number of, with the help of n bits, how many standard levels we can make, which is 2 to the power of n. So the number of levels, the maximum number of levels can be 2 to the power of n, and minimum it can be 0. So therefore it is going to lie between the 0 to 2 to the power of n. So therefore L is going to lie between the 2 to the power of n. Means the number of levels can be lesser than 2 to the power of n, but not more than n, because with the help of n bits we can make a number of levels of only 2 to the power of n. So therefore the number of levels can lie between less than or equal to 2 to the power of n. So in the question they are given the number of standard levels are 128 less than or equal to the power of n. So 128 means 2 to the power of 7 less than or equal to the power of n. So by comparing both this we are going to get n is equal to 7. So with the help of n is equal to 7 bits, means for each and every sample we have to go for the 7 bits. So therefore in the question they are also given that here the maximum bandwidth, means the channel is going to have a bandwidth of 4 kHz, means the message signal frequency must not be more than 4 kHz, means it has to be up to 4 kHz only. So therefore maximum message signal frequency is 4 kHz. So therefore the sampling frequency, so by using the sampling frequency which is 2 into f max, which is 2 into 4, which is 8 kilohertz. So now we need to find what is the bitrate. So bitrate is equal to n into fs. So n value we know, which is the number of bits per sample is 7, and fs is sampling frequency, which is 8 kilohertz. And if you do the multiplication, 7 8s are 56 kilobits per second. So in 1 second 56 kilobits are being passed. So therefore the unit of n is number of bits per sample, and the unit of fs is nothing but the fs is called as the sampling frequency, means the number of samples per second. So therefore if you do the multiplication, this both get cancelled. So therefore the unit of the bitrate is bits per second. So this is the correct solution of this question. So we are going to solve the 125 question. See the question here. A binary channel with capacity of 36 kilobits per second is available for PCM transmission. If the signal is band limited to 3.2 kilohertz, then approximate values of the quantization levels and the sampling frequency. So in the question they are given the bitrate is equal to 36 kilobits per second, and also they are given the maximum message signal frequency is 3.2 kilohertz. So based on these two things, we need to find what is the number of quantization levels, means L, and also we have to find what is the sampling frequency. So out of the four options, option D is the correct solution of this question. So let's solve this numerical. So in the question they are given that the bitrate is equal to 36 kilobits per second, and also they are given that the maximum message signal frequency can be allowed is 3.2 kilohertz. So based on these two data, we need to find what is the number of standard levels L, and also the sampling frequency we need to figure out. So these are the four options. The first one is number of levels, and the second thing is the sampling frequency. So therefore if you see carefully here, bitrate is equal to n into fs. This formula we have already used also. So bitrate is equal to n into fs, and fs, the sampling frequency must be always greater than or equal to twice of the maximum frequency. So here we are going to use the minimum sampling frequency. Let me assume fs is equal to 2f max. So here minimum sampling frequency I am going to use here. So basically the number of standard levels will be less than or equal to the power of n. So therefore here now I am going to use the log base 2. So therefore log base 2 means log L base 2 must be less than or equal to n. So therefore here n, so n is equal to bitrate is equal to n into fs. So n is equal to bitrate by fs. So in place of n I substitute bitrate by fs. So here fs is equal to again 2 into f max. So therefore in place of fs I am going to substitute 2 into f max. So here log L base 2 less than or equal to bitrate by 2 into f max. So I know the value of the bitrate, which is 36 kilo. See, 36 kilobits means 36 into 10 to the power of 3. 2 into f max is 3.2 kilohertz, means 3.2 into 10 to the power of 3. So finally I am going to get the value of L. The number of standard levels is less than or equal to 49.35. So if you see carefully in the options, the levels they are given either 32 or 64, but we got the number of standard levels must be greater than or equal to 49.5. It has to be lesser than the 49.5, but 64 is greater than 49.5. So therefore B and C are not the correct answer. So therefore here the levels should be lesser than the 49.5. So therefore 32 is lesser than 49.5. So therefore we are going to assume the number of standard levels are 32. So therefore here I am going to assume the number of standard levels are 32. So therefore L less than or equal to 2, L less than or equal to 2 to the power of n. So L is equal to 32 to the power of 2n. So 32 means 2 to the power of 5 less than or equal to 2 to the power of n. So n is nothing but 5. So the number of bits per sample now we have got, which is 5. So based on this, the bitrate is equal to n into fs. So bitrate we all know, which is 36 into 10 to the power of 3, and n is 5. Just now we have calculated into fs. So based on this, if we calculate fs is equal to 7.2 kilohertz. So here we got the value of L, which is 32, and fs is 7.2 kilohertz. So only D option we have got. So D is the correct solution. See, let me also check whether the sampling frequency is greater than or equal to twice the maximum message signal frequency. So fs is equal to 7.2 and f max is 3.2. So 2 into 3.2 is nothing but 6.4. So we can conclude that whatever the sampling frequency we have taken, it is greater than or equal to twice the message signal maximum frequency. So therefore option D is the correct solution of this question. So now we are going to solve the 126th question. See the question here. The following events will not happen when quantizing noise is decreased in PCM. So when the quantizing noise is decreased, then what is the thing which is not going to happen? So here out of the four options, option C, decrease in channel noise, means the channel noise will remain same but it will not decrease. So therefore option C is the correct solution of this question. See, option A, option B, option C and option D, everything now we will discuss in detail. So now we will discuss each and every option in detailed manner. So in this question they are given delta is nothing but quantizing noise power. When this quantizing noise power will decrease, what will happen and what will not happen, we will discuss in detail each and every option. So basically before I solve this one, let me know what are these variables. Delta is called as the quantizing noise or step size of the quantizer, and R is called as a range of the message signal, which is V max minus V minimum. So we can say it is V peak to peak voltage, and also L is called as the number of standard levels or the quantizing levels. So N is called as the number of bits required to transmit each sample, means L is called as the number of bits per sample. So in the option, see, in the option A they have said that increase in the number of standard levels. So increase in the number of standard levels. So let me say this is the number of standard levels. Let me see why, whether this is correct or wrong. So in the case delta, the basic formula delta is equal to range by L, the number of standard levels. So L is nothing but 2 to the power of n. So if you see carefully here, they are given that delta is going to decrease. So therefore the denominator must increase, then only the overall will decrease. So therefore we can say here L has to increase. L has to increase, then only this delta will decrease. Means L increases means the n value must increase. Then only we can say the delta value decreases. So therefore L is called as the number of standard levels. So when delta decreases, we can say the number of standard levels increases, or we can also say the number of bits are increases. Yes, the option A is correct. Means option A is correct. Whenever the delta decreases, yes, the number of standard levels will increase and also the number of bits will increase based on this formula also. So and option B, what they have told is increase in bandwidth. So let's see whether this is right or wrong. So bandwidth is equal to, so bandwidth is nothing but bitrate, which is n into fs. See, as the n is increases, so therefore the bandwidth is also increases. Yes, so as the n is increases, so bandwidth is also decreases. So it's also correct. And now see, decrease in channel noise. So let's see whether the decrease in channel noise will happen or not. We are going to check. See, this is a channel noise function with respect to x here. So this is a minus delta by 2 and this is a delta by 2 and this is a 1 by delta. If you take the area of this graph, so area of this graph is equal to width is equal to delta and height is equal to 1 by delta. It's always 1. So it is always 1. So therefore no matter whether you decrease, if you decrease the width, the height will increase, so the overall area will always same. So we can conclude that this area is going to give you the information of the noise power. So therefore channel noise, the area is going to give you about the channel noise, means whether you increase or whether you decrease, the area is always constant, which is equal to unity. So we can conclude that the channel noise will always remains the same. It will not increase or it will not decrease. So therefore C is the wrong one. So therefore we can conclude that here C is the wrong one, means in the question they have asked what will not happen, means so therefore it won't decrease but it will remain same. So we can conclude that C is the correct answer for this solution. So here in the question D, the option D, they have said that decrease in randomness due to difference in digits in an actual signal at an instant. So therefore I have already told you regarding this one, quantizer. So in the quantizer here we are going to get an infinite number of samples of amplitude samples, but here we are going to get the standard levels of samples. So here when delta decreases, we already know when delta decreases, L is increases means the number of bits are also increases. So the number of standard levels are increases. Suppose let me assume this is 0.2. The original signal value is 0.2. Suppose if the number of levels are less, means suppose here it is 2 volt. So 0.2 now is approximated as 2 volt when L is less. Suppose if the number of levels are increases, means it can become now 1 volt also. So now the difference between 1 and 0.2 is now decreased when compared to 2 minus 0.2. So again if you increase the L, what will happen? It will become now 0.5. So therefore the number of level increases means the signal will be accurately simulated. So therefore here the difference goes on decreases. So as the L increases, the difference between this actual value of the signal and the quantized value of the signal has been decreased. So 2 minus 0.5, 0.2 is greater and 1 minus 0.2 is still lesser and 0.5 minus 0.2 is still even lesser. So therefore as the levels is increases, we can exactly or we can evenly approximately or accurately we can approximate this actual signal into a quantized signal. So all this is going to happen whenever the delta quantizing noise power will decrease. Only thing which is not going to happen is there will be no decrease in the channel noise, but it will be always, the channel noise will be always constant. So finally what I am trying to say is, whenever the quantizing power will decreases, the number of levels will increase, the bandwidth is increased, the number of bits will increase, the channel noise will remain constant, and also here decrease in randomness means that the error value goes on decreases. The error between the actual value and the sample value and the quantized value will goes on decreases. So this is all about this question. Now we are going to solve the 127th question. See the question here. A signal is passed through a low pass filter with cutoff frequency of 10 kHz. So the minimum sampling frequency is. So here they are given a question with the low pass filter is going to have a cutoff frequency of 10 kHz. So we have to find what is the minimum sampling frequency. So out of the four options, option A 20 kHz is the correct solution of this question. So let's solve this numerical. So this is the transfer function of an ideal low pass filter. So here the transfer function says that h of f is equal to 1 for mod f less than or equal to fc, and it is 0 otherwise. So basically if you see carefully here in the question, they are given the cutoff frequency is equal to 10 kHz, means the maximum message signal frequency which is possible is only which is fc. So therefore maximum message signal frequency is now 10 kHz, not more than that. So therefore here we have to find what is the minimum sampling frequency we need to figure out. So always the sampling frequency must be always greater than or equal to twice the maximum message signal frequency. So therefore we need to find what is the minimum sampling frequency. So minimum value is twice the message signal maximum frequency. So 2 into FM max is 10 kHz. So 2 into 10 is equal to 20 kHz. Means if you do the sampling below the 20 kHz, yes, there will be a aliasing effect. Means the high frequency message signals will become now low frequency, and the low will become high. So it is a changing of the frequencies. But if you do this one more than this, there will be no aliasing effect. Then by using the low pass filter we can get back the original message signal. So here the minimum sampling frequency is 20 kHz. Minimum sampling frequency is also called as the Nyquist frequency or the Nyquist rate. So now we are going to solve the 128 question. See the question here. The Nyquist sampling interval for the signal sync 700t plus sync 500t. Here see, this is a signal for the signal x of t. We have to find what is the Nyquist sampling interval. Time period we need to figure out. So out of the four options, option C 1 by 700 seconds is the correct solution of this question. So let's solve this numerical. So for the signal, this is a signal x of t which is given in the question, which is sync 700t plus sync 500t. So for the signal we have to find what is the Nyquist sampling interval we need to figure out. So basically sync kt is nothing but sin k pi t by k pi t. So therefore here now I am going to write in that format. So therefore sin 700 pi t by 700 pi t plus this is sin 500 pi t by 500 pi t. So here this is nothing but 2 pi fmt. So therefore 2 pi fm is equal to 700 pi. So therefore fm1 is equal to 350 Hz. And similarly for this signal, if you see carefully, this part I am going to take here. So 2 pi fm2 is equal to 500 pi. So therefore fm2 is equal to 500 by 2, which is nothing but 250 Hz. So here always the sampling frequency must be greater than or equal to twice the message signal maximum frequency. So therefore here there are two message signal frequencies. So therefore out of these two we have to take only the maximum part. So therefore I want to know the Nyquist frequency is nothing but minimum sampling frequency. So minimum sampling frequency is called as the Nyquist frequency, which is twice the message signal maximum frequency. So basically here fs minimum is equal to twice the, so there are only two message signal frequencies. Out of this we have to take only the maximum message signal frequency. So out of this 350 and 250, the maximum value is 350. So therefore 2 into 350 is nothing but 700 Hz. This is a frequency, but now I need the time interval. So time period is equal to 1 by frequency. So 1 by 700. So this is the Nyquist sampling interval. So in the question if they ask what is the Nyquist sampling rate, means 700 Hz. In the question they ask Nyquist sampling interval means 1 by 700 seconds. This is the correct solution of this question. Now I am going to solve the 1009 question. See the question here. If the number of bits per sample in a pulse coded modulation system is increased from 8 to 16, then the bandwidth will be increased by how many times? So in the question, if the number of bits is increased from 8 to 16 in a pulse code modulation, then what is the bandwidth nature? Whether it will be increased by how much factor we need to figure out. So out of the four options, option A 2 times is the correct solution of this question. So let's solve this numerical. So the bandwidth in the PCM is going to lie between the RB is nothing but half of the bitrate and bitrate. So therefore the bandwidth of the PCM is going to lie in this range. So I am going to assume the minimum bandwidth is nothing but RB by 2. So RB is called as the bitrate. So bitrate formula is N into Fs. N is called as the number of bits per sample and Fs is called as the sampling frequency, means the number of samples per second. Number of samples per second. So therefore if you do the multiplication, we are going to get the bitrate. So bitrate by 2. So here when n is equal to 8, let me assume the bandwidth here. The bandwidth is BWM1, which is n is equal to 8 Fs by 2, which is 4 Fs. And similarly when n is equal to 16, this is the bandwidth 2, which is in place of n substitute 16. So 16 Fs by 2 is equal to 8 Fs. So now I am going to do the division of these two things. So therefore bandwidth 1 by bandwidth 2 is equal to 4 Fs by 8 Fs. So Fs is going to get cancelled. So 4 1s are 4 2s are. So therefore the bandwidth 2 is equal to twice the bandwidth 1. So therefore we can say that the bandwidth is increased by 2 times. So here if n is increased from 8 to 16, the bandwidth also increased by 2 times. So this is the last question of this lecture. See the question here. In differential PCM, in differential pulse code modulation, each word indicates. So out of the 4 options, option B is the correct solution of this question, which says that difference in amplitude between a current sample and the previous sample. So therefore here each word in differential PCM is nothing but it is going to tell you about the difference in amplitude between the current signal, current amplitude value minus previous sample value. So therefore option B is the correct solution of this question. So let's solve this numerical. So this is a block diagram of the differential pulse code transmitter. So basically it is going to consist of the same thing, but extra thing, there is a feedback here. So it is same as the PCM, but extra thing is there is a feedback here. So it's a sampler, quantizer, encoder. So with this feedback here, suppose this is a new signal, new current value, new current sample value. So because of this delayed, it is going to come some late. So therefore new sample value is nothing but current sample value. This current sample value minus previous sample value, it is nothing but here this is the new sample value. So therefore here, because of this feedback loop which is present here, the new sample is equal to current sample value minus that, because of this delay it will become now come here. So previous sample value. So therefore new sample value is equal to current sample value minus previous sample value, that is used in this quantizer. So with the help of this quantizer, again same thing here, this is the NB is called as the number of bits which are used in the DPCM transmitter. So basically the final what I am trying to say is nothing but here in differential pulse code modulation, always the new sample value is equal to current sample value minus the previous sample value, because of the feedback loop is present in this circuit. So by this lecture we have successfully completed the 130 questions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notification comes on mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started.